Alright, in this video we'll be looking at the variance and standard deviation of a random variable. Okay, we've talked about this random variable a few times now, but at the very beginning we asked what the average or mean of the random variable in the long run would be. We worked that out. That's what we called the expected value. That's what that was all about, right? The long-term average or mean of the random variable. Then we asked what a sensible measure of spread would be, and that's what variance and standard deviation are all about. Okay, so what might we mean by spread? Well, if we get x, the fair die random variable, we ask for a bunch of numbers, say 20 of them I think, and record the results on a plot. What we're asking is how spread we expect these numbers to be. Again, we're not dealing with this particular outcome or any particular set of outcomes. It's how spread we expect in general, in the long run, the numbers to be. Okay, by comparison, if we get, say, a biased die, a loaded die that, say, makes the 6 appear way more than any other number, we might get a plot that looks like this. Then because we'd expect maybe to get a cluster of all these 6s, maybe the data should be maybe less spread out on average. I don't know, right? Just a disclaimer, it's not generally true that loading your die leads to a lower spread. I actually tried a few of them, and loading your die quite often leads to a higher spread for a variety of reasons. But it is definitely true that if you heavily load it towards one number like this, you will, in general, lower the spread. Okay, so what will be a sensible measure of this spread idea? Okay, so it actually might be clearer to think about these ideas on a loaded die. Okay, we'll load it so that 5 and 6 are twice as likely as the others, but otherwise it's even. Okay, now before we fill in the probability distribution, just notice I've got a big X in the first row of the table here. That is not normal. If I wanted to be super careful, it probably should be the little green X. Okay, what I mean by that is the big X random variable could give you those green numbers from 1 to 6. But remember, it's just the magic box that produces those numbers, not the numbers themselves. Okay, I'm writing it this way because it makes what we do next a little bit easier. I'm cheating a little bit, alright? But in future, in the questions and stuff you do, you'll probably be seeing that first row labeled with a little x. So I just want to warn you, give you a heads up ahead of time, okay? Alright, I've tried really hard to be consistent with my colouring, by the way, I hope you've noticed, across this whole series, so hopefully that helps avoid any confusion, but let's move on. Okay, so since the probabilities must add to 1, alright, that means the chance of getting the numbers 1 through to 4 must be 1/8 each, while 5 and 6 are 1/4 each, right? And that makes it so that 5 and 6 are double the chance of numbers 1 through to 4. Okay, and this number line down the bottom here illustrates all possible outcomes, and we want to measure some sense of spread, right? But where do we measure from, right? What's our reference point to measure things from? It would seem to make sense to measure how spread out things are around some kind of central point, some kind of mean value, right? And so it would make sense to start by calculating the expected value of this random variable. So all the numbers from 1 to 4 get multiplied by their probability, 1 out of 8. So we can put the 1 out of 8 out here in brackets, then fill it in by totaling up the 1 through to 4. Then 5 and 6 have probability 1/4, so we can put the 1/4 outside the brackets, then fill it in with the 5 plus 6. Turns out the answer here is just 4 when we do this, so the mean, the average of this random variable, is 4. So it makes sense to think about how spread out things are around the number 4. Okay, so we take all possible outcomes from 1 to 6 and calculate how far away they are from the number 4. And the way to see how far apart two numbers are is, well, to subtract them. The difference between them is a subtraction. So we'll make this new table row, and in this row we'll calculate the value of x minus this expected value of 4 to keep track of how far away every possibility is from this expected value. Okay, so if we do that, we get 1 minus 4 is negative 3. 2 minus 4 is negative 2. 3 minus 4 is negative 1. 4 minus 4 is 0. 5 minus 4 is 1. 6 minus 4 is 2. Okay, so those are our distances. Now, eventually we'll want to put these numbers together to see what I guess we expect the spread to be on average, but here's a problem. Say if we put these distances of 2 and negative 2 together and we combine them, well, 2 and negative 2 will just cancel each other out, right? So to properly measure distance, we shouldn't have negatives there. They all need to be positive, so that we're purely tracking how far away from that mean value we are. Okay, now it's tempting to just, I guess, turn those numbers positive, and sometimes people do that, right? There's a name for that, but we don't study that here. But to just turn negatives positives actually comes at a cost, right? Because when we just do that, right, I hope you can remember, right, we call that an absolute value. Alright, and you would have seen previously that absolute value functions are not the nicest things to work with, mainly because you can't differentiate them. There's a sharp corner there. Alright, so the cost is this: you lose the ability to use calculus, which then takes away a lot of the tools you might want to use on these functions further down the track. Okay, so later everything's going to come together, and to be able to use calculus is a very helpful thing. Okay, so that's why generally we don't just turn those negatives positive. And so what's a nice differentiable way of making things positive? Well, the simplest way is to square them. Alright, and so let's do that. If we square everything, we get the numbers 9, 4, 1, 0, 1, and 4. And so now we can almost treat this last row itself as a random variable. As a random variable that measures how far away x is from its own average. Okay, and everything's positive now, so it's going to be able to fairly do that. Okay, and sure, there are some repeated values, but you can still think of it as a random variable that could give you 9, 4, 1, or 0, each with their own probability. Okay, and what the variance does is it calculates what you expect this spread to be. And therefore we calculate the expected value of this bottom row random variable. Okay, and so we're going to repeat very much the same calculation as what we did for the expected value of just x itself, using those same probabilities, but now with the square distances from the average being used instead of the original values of x. And this gives us a variance then of 3. Okay, and that's the most commonly used and useful measure of spread. Notice though that in the working we had to square all those distances, but in many cases, say for the sake of keeping units consistent or keeping the scale the same, we want to sort of rescale that back to the original. So what we call the standard deviation is then just the square root of the variance, okay, which will undo the effect that squaring had. Okay, so in this case, the square root is just the square root of 3. Okay, and the symbol we use for standard deviation is the little Greek letter s, okay, also a sigma, but lowercase sigma, which looks like that little guy there. So that's the variance of a random variable. It measures spread by averaging how far away each outcome is from the mean, from the expected value. So the formula looks like this. We saw it before already. The expected value of x's square distance from its own mean. Calculating this like we just did it is quite fiddly. As you saw, there were quite a number of steps. We had to make up 2 new rows on our table. You could do that, but there's a way of simplifying this calculation using the properties of the expected value that we saw last time. So the first thing we can do to simplify this is to expand out the square. Okay, so we get x squared minus 2x e of x plus e of x all square. Then we can split that big orange expected value across all the additions and subtractions. That's one of the things we saw last time. So each piece can go in its own separate orange expected value thingy, and we can deal with each of them separately. We'll leave the first one alone, this e of x squared guy, right? And now very carefully look at what's inside that second bracket. Right, x is a random variable, but notice that yellow e of x. E of x is not actually a random variable, it's a constant number, because e of x means the expected value of x. That's not a variable, right? It's a constant. In our previous example, it was the number 4, right? The mean of the random variable, the average. Okay, so actually both the 2 and the yellow e of x are just constant multiples, and so both of them can actually fly outside the bracket, leaving only the random variable x inside the orange bracket. Okay, then the last big orange bracket there only contains the yellow e of x or square, but as we just said, that's a constant number. Alright, well, what's the expected value of a constant number? Well, it's just the number itself. I mean, if you had a magic box whose job was to hand you the number 5 every single time, then his expected value would of course just be 5. So that means that the orange expected value at the end there doesn't do anything, right? We can just get rid of that and leave it as e of x all squared. Okay, I think that was the hardest step. Not long to go now. We'll leave the first term alone again. For the second one, we'll keep the -2, but notice how we just have 2 copies of e of x multiplying together, right? And when you multiply 2 copies of the same thing, we can just join them together as e of x all squared then. And then we bring the last term down as just e of x all squared again. Okay, so now that last term can simplify. Okay, if we minus 2 lots of e of x all square, then add 1 more back in, we end up with just -1 or -1 e of x all square. Okay, so that's the formula that makes calculations by hand a lot easier actually. It's the expected value of x square minus the expected value of x all square. Okay, I'll show an example of this. I know it might be a bit tricky seeing it just in symbol form here. I'll show you an example in a sec, right? But also remember the standard deviation, called sigma, is just the square root of this. They both measure spread, but the standard deviation preserves the units and scale of the original random variable x. Alright, we'll finish off our whole series, I think, for now, by doing an example from NES's sample HSC thingy that they published. It says a discrete random variable has this probability distribution, and by working out m, we want both the expected value and the variance. So to work out m, remember the total of all probabilities must be 1. So all those guys in the pink box add up to 1. Forcing m to have to be 0.1, okay, because 0.1 plus 0.2 plus 0.3 plus 0.4 equals 1. Now for the expected value, we calculate that by multiplying each outcome with its probability and adding them up. So 11 times 0.2 is 2.2, 12 times 0.3 is 3.6, 13 times 0.1 is 1.3, 14 times 0.4 is 5.6. In total then, we add them all up. That gives us 12.7 as our expected value. Okay. Then for the variance, we'll use the calculation formula we just came up with. That's the expected value of x squared minus the expected value of x all squared. Now, the expected value of x is what we just calculated, so we know that yellow one already. Okay, what we're missing, the only ingredient we're missing here is the first term, which is the expected value of x squared. Now, how do we work that out? Well, what is x squared? What values could x squared be? Well, we can just zoom back in on the x's and then just square them all. So 11 square is 121, 12 square is 144, 13 square is 169, 14 square is 196. Okay, then we take the expected value of these guys using the same set of probabilities. So if we go, 121 times 0.2 is 24.2. 144 times 0.3 is 43.2. 169 times 0.1 is 16.9. 196 times 0.4 is 78.4, and they add up to 162.7. Okay, so then finally, this variance would be the 162.7 minus the yellow expected value thing, the 12.7 it must be, or square. Okay, and so the 12.7 gets squared, you subtract that from 162.7, and that gives us 1.41 for the variance. Okay, so that's all for this video series for now. As always, if you have any questions, feel free to ask. Thanks for watching, and I will see you around. Bye.